Hi, my name is Mike Jasper. I'm really pleased and honored to be able to give a Donuts.js talk today about performance and making very fast websites. This is a screen recording of that talk. Unfortunately, there was a technical error during the presentation, so I've gone back and re-recorded this, and I'm trying to make this as close as I can to the actual slides. To the actual presentation. So the most important thing to take away from this presentation is that performance is about getting the most bang for your buck. There are lots of things you can do to make your website fast, but as we know, premature optimization is one of the roots of all evil. And so what I've done is organize these slides in a way that should show the most bang to buck things you can do at the beginning, and then as they move on, get more difficult to implement, but give you a little less. Like if you just need to eke out a little bit more performance, that's what you'll get at the end, versus things that everybody should be doing at the very beginning of this presentation. So some of the topics are images, asset loading, CSS, JavaScript, JavaScript usage, using libraries or not, ways we can timeline and profile that. We're going to talk about caching and compression, and some infrastructure architecture things as well. So one valid question to ask is, why should you care about performance? This slide shows a speedtest.net. This morning in the office got 93 megabytes down. I think it was about 50 up. So an insanely fast internet connection. And when I loaded LDS.org today, I received my first byte in about 8 milliseconds. Or excuse me, 18 milliseconds. That means in 18 100ths of 1 second, I got the first response back from the server. This is insanely fast. Now at home, I have a little bit slower internet. I have DSL, which has 5 megabytes down. I know, guys, that's pretty low. But still, I don't run into big performance problems. So why do we care about performance? We have real fast internet around us. Our phones have LTE. Why do we need to have really fast performant websites? There's a website where you can type in a website address and it will show you how much that website costs in relative amount in different countries around the world. So I've used one that's kind of middle of the road. It's not perfect, but it's not bad either, Mormon.org. The homepage of Mormon.org is 1.39 megabytes. And then in the graph right below it shows how much that costs in relative amount for someone living in that country. So you can see the first country there, Vanuatu. Vanuatu is a small island in the South Pacific Ocean. And their internet costs and speed is such that 1.9 megabytes in Vanuatu cost 5.79% of an individual's daily budget. I mean, if you had $100 to spend for every day, loading this one web page just cost $5.79. You can see that quickly goes off. Liberia, Papua New Guinea, Angola, Ethiopia, these are all places we would expect to have slow internet connections. And so, do we really need to care about Vanuatu or Liberia? The answer is yes. Vanuatu is a place where there are members of the church. There's a mission. There are 4 districts, which are equivalent to stakes. There are 11 branches, which would be like wards. Hundreds of members. There's missionary work going on. So even if you have internal-only applications, these are still being used in places like Vanuatu. You know, if a bishop sending a missionary recommendation system, patriarchal blessing systems, leader and clerk resources, these are all tools that are not geared toward the general public, like LDS.org or Mormon.org. They're geared only for our internal church audience. However, they're still being used in places around the world like Vanuatu. But it's even closer to home. This is a picture I took on the train a couple weeks ago. I ride the train to work every day. So I saw a young lady on the train, and she was using a BlackBerry phone on the train Wi-Fi. And so I somewhat creepily took a photo of her without her knowing. Because it really struck me that even in Salt Lake City, one of the tech hubs of the nation, people are still running old devices on slow networks and it's not something that they can do much about. And so they're beholden to the performance of our web applications. It's important to not consider ourselves as the rule, but as the exception with our 100 megabyte down internet speed. We need to remember that we are the exception, not the rule. So let's dive right into the topics. The first topics and first couple are about images. The first one is about optimizing images. This is a picture taken from the homepage of LDS.org. It is 82 kilobytes. That's actually pretty good. That's not a terrible image. We've seen them before in the 1 megabyte range, so they did a great job optimizing this. But I wonder, can it be better? Using Photoshop, a tool which some of us have access to, we can save for web, which allows us to choose the file type and choose quality, compression types. So using Photoshop, I was able to save this image down at 75% quality and save about 10 kilobytes of data. Now 75%, you're thinking, you lose 25% of an image quality? Is that really what you want to do? It's really almost imperceptible to the human eye. My general rule is slide the quality down until you notice a difference and then take it back up by about a third. So using that rule, we arrived here at 75% and save 10 kilobytes on the image. Now that's just image compression. There's another part of the image, metadata, which we can strip out too. Images contain several kilobytes of data, which can include GPS coordinates, the type of camera, the type of lens, the file size. And this is text data that the image can use to tell other systems about itself. So using this free program, Image Optim, we're able to remove a couple kilobytes just in metadata. Another part of optimizing images is making sure you use the right file size, the right file type for the right image. We have photos, graphics, screenshots, animations. There are a lot of different uses for image assets, and not every file type is right for every situation. JPEGs are perfect for photos. They have great photo compression and do well when an image contains lots of different colors. This specific image, also from the homepage of LDS.org, we're able to save as a JPEG at 83 kilobytes. If you use a PNG, that jumps all the way up to 229 kilobytes. PNGs are perfect for screenshots or for graphics, charts, things like that, and images that might be large but contain relatively few colors. If we save this as a GIF, it's 113 kilobytes, and the perfect uses of a GIF are nothing. GIFs are almost never used or never useful. There are almost no circumstances that you should want to use a GIF. If you want to have transparency, use a ping. If you want animation, use HTML5 video. HTML5 video is surprisingly heads and tails better performance than GIFs when it comes to animation. Now you're wondering, these are all images that I have control over. What about images that content contributors might add, like a blog or an article or something like that that's written by another person and then uploaded to my site? The key here is to use a server-side image service. ImageMagick is a very popular one that's available in almost every platform. We have one internally that we have with LDS Publisher. This is a link to that. You can use that, and it'll do cropping and it'll do compression. So you can have a content contributor upload an image with their article or what have you, and it's sent to this service fixed, and then it can come back. All right, moving on, still about images though. The next step is to remove images if you can. We spend a surprisingly lot amount of time arguing about this framework versus that framework, how much JavaScript we want to load with the page, but we forget JavaScript isn't really that big compared to images. For example, banana.jpg is 33 kilobytes. That's bigger than jQuery. That's bigger than Bootstrap's JavaScript library. So if you can remove one single image from your site, that might make more of a difference, at least in load time and download speed, than removing an entire JavaScript library. Now that's not true when it comes to execution for the speed and the speed and the performance concerns that JavaScript libraries have. So another part of images is to lazy load your images. If you can't remove an image, you can remove it at least from downloading when the page loads. For example, if your site has 10 images on them, have the first one as a normal image and then load the rest of them through JavaScript. That way the user only initially downloads one image, but as the page renders with JavaScript, they download more depending on where they've scrolled to on the site. Now it's fairly easy to implement if you want to write your own library. This is actually something that's interesting to do and it's fun to do. I'd recommend write your own lazy load library and learn from it, and then go find one that's industry recommended and has been tested and use that instead. But it's fun to do and they're not too hard to make. So the basic idea is that you have an image tag, and inside that image, instead of having a source, you might have a data attribute, a data source, and a class of lazy. And then next to that, a no-script tag containing the normal image, so a search engine or a reader or a scraper or someone without JavaScript, bless their hearts, could still get to your image. And then some pseudocode that would walk through how this would work is whenever the window is scrolled up or down, you'd loop through the images and you'd wonder, does the image top approach the bottom of the viewport? Or alternatively, you could say, does the side of the image approach the side of the viewport if you're scrolling horizontally? If it does, set the source attribute of the image to the data source attribute, and then your browser will go ahead and load that image. So that way, when you first load a page, you might only have, one image, two images load. As you scroll down, they're loaded in, and so you get that performance win. All right, we're done with images. The next section is about CSS and JavaScript loading. So CSS is not blocking, JavaScript is blocking. That's the short story. The long story is that, think about when a browser downloads a web page. The first thing it gets is HTML, and it's just raw data. It's text that it gets from a server. When it receives that HTML, it parses it and builds a DOM, a document object model. When it builds that DOM, it goes through and places children and parents and builds this kind of a tree. And when it discovers a CSS or a script tag, it continues loading that. I think when a browser sees a CSS tag, what can that browser, or what could that CSS do to the DOM? CSS can change the size of things, it can change the position of elements, it can move elements outside the flow, you could show and hide things, but nothing CSS can do can really affect the underlying DOM. And so it downloads that and it keeps downloading asynchronously while it's parsing and building the DOM. Now if your browser parser finds a JavaScript, either external JavaScript or inline JavaScript, it has to stop. Because what can JavaScript do to the DOM? It can delete nodes, it can add nodes, it can wipe out the entire page, it can redirect to a different URL. Your browser now has no way of knowing how the DOM is going to be affected by this JavaScript. So what it does is it pauses building the DOM, downloads the JavaScript, executes it, and then continues on its way. So one way of ensuring that JavaScript is not stopping the page is by putting it at the bottom, putting your CSS at the top. Here's a little inside joke for you Utah Jazz fans. I know there might be a few of you in the audience. JavaScript is blocking. There you go. Speaking of scripts, so you've got your scripts at the bottom, but you still have to load all those scripts before they execute. Well, ask yourself a question. Do you need those scripts to be there for the page to function, or is your site progressively enhanced, meaning it can work just as bare HTML, and then it's built on by JavaScript to enhance that functionality? That's the recommended way. Our sites should all be done that way. And so if they are, we can use this asynchronous loading of JavaScript in order to defer that download time and render the page faster. Now the bare bones, absolute, most simple way you can do that is by including an async keyword. The tiniest thing. You have a script tag, so script source, javascript.js, async. That's it. what async tells the browser to do is oh, I found a script tag, but I'm going to put it off to the side and continue parsing the rest of the page. Once the page is finished, it's going to take those scripts it found, downloads them asynchronously, and executes them in the order they're returned. So one important gotcha is that they're not executed in the order that they might be on the page. So where this can bite you is if, for example, you're loading jQuery and then you're loading plugin A, plugin B, plugin C. There's no way of guaranteeing that plugin A is not downloaded and executed before jQuery, the main library is, which can really screw things up. So one way to overcome this is to use a script loading library or micro framework. There are dozens of them, literally, and the essence is pass some scripts. It'll download them asynchronously, but execute them synchronously, so you can ensure the order that you need to have your scripts function correctly. And then you pass a success callback or a fail callback, or anything like that. And different scripts loaders were built for different purposes, and so their implementation may be different from each to each. So it's important to find one that works for your project and find the one that'll work with your set of requirements. Okay, still on JavaScript, you've loaded the library. The next step is to toss it out the window. I would wager that most of the things we do with jQuery are adding a class to an element, attaching an event listener, hiding something. Maybe we're doing animation, on a scroll. We're doing a pop-up tooltip or something like that. So ask yourself a question: do you really need jQuery to do those things? So the picture on this slide is a paving machine. If you look, there are a big pile of bricks on the top, and a huge multi-ton machine, and out the bottom come this paved, beautiful, interlaced road. Now this is a slow process. It can take hours just to move a few feet. So I would say that jQuery is like a paving machine. It's big, it's slow, but if you need it, it's really convenient. But you have to ask yourself, truly, do you need the paving machine to pave over browser inconsistencies, or in your application would something like a dirt bike work a little better, faster, cheaper, easier to use, and your users don't have to download a paving machine? So these are some examples of what code would look like written in jQuery and written natively. This is to select an element or a set of elements, to attach an event listener to an element if you wanted to add a click function or something like that. And you notice it is a little longer. I acknowledge that the code you write can be longer if you're writing it without a library. This is to add a class to a set of elements. Like I said, the code is a little longer what you're writing, but you have to realize whatever you've written here in the native implementation is already what jQuery is doing behind the scenes. So you haven't saved any code except you've saved your fingers from writing it. But from a performance point of view, you haven't saved anything from going down to the users by doing a library. In fact, you've probably increased the amount of code you need to write by 100 by adding a library that you don't need most of it on there. And it's also important to know that there's no magic behind the scenes. jQuery, when it comes right down to it, is native JavaScript. It's just native JavaScript that's been performance tested and increased to handle a number of use cases, some of which you may not need. There are some considerations. It's not a hard and fast rule. There's some things that are pretty hard to do without a library. One example would be parent element selection. If you're in the DOM and you need to find a parent that has a certain class, doing that without a library, you'd need to create some sort of recursive function that would walk up the DOM and find an element that matched. Another example would be if you need to have Ajax in a browser like an old IE. IE handles Ajax a little different prior and equal to IE 8. So for those reasons, it may be that it's in your best case to use a library. But if you don't have those certain set of problems, I'd suggest you look into ditching it. The next step is to minify, uglify, and concatenate your code. Minify is to remove white space, line breaks, comments, things that are only needed by the developer. You don't need the user to download. Uglify is called obfuscation as well. It renames variables and can rewrite functions into really small forms that would be more difficult to debug, but shorter or less footprint for a user to download. Concatenation can combine any number of files into one file, so your user, you know they're going to need to download 3 or 4 things, put them in one file. It still costs the same in page weight, but you only have to make one HTTP request. And this is prime for integrating into your build process. If you're doing this and you're not doing it using Grunt or Gulp, that's not the right way to do it. So you need to integrate this. There are a number of plugins you can do that will minify, concatenate, uglify, all in your build step. And once you set it up, it's out of mind. It just happens automatically, auto-magically. All right, the next tip is to throttle your JavaScript events. So think about when a user's interacting with a web page, the things they might do that you could bind events to. They might scroll on the page. They might resize a window. They might move their mouse. These are events that are based on user input, and so they can be fired hundreds and hundreds of times, even in 1 second. Think about a scroll. How many pixels does a user scroll at a time? It might be 2, or it might be 200 or 2,000. So some browsers will take each of those changes and fire a scroll event, or you move your mouse around in a circle. How many times is your mouse moved? Well, it's hundreds and hundreds of times a second. Your browser is going to fire events for those. So I've got a demo that shows how we can use throttling or debouncing to take away the pain of those events. I'm going to go ahead and reload this page. So this is a simple example. I have 3 event listeners, one for resize, one for scroll, and one for mouse move. And each of those listeners is handled in a different way. Resize is a native or a naked function. Scroll is debounced, and mouse move is throttled. Debounce means that the function is only, or the callback function for the event listener is only fired one time when the event stops happening. So if you scroll, it's going to be fired once when they stop scrolling. Throttle means that it'll keep firing, but it'll fire at lower intervals. You can say only fire once every 500 milliseconds or only fire once a second. So here's an example. I'm going to go ahead and move my mouse around, and you'll notice that it's only firing once every 500 milliseconds. You can see that based on the counter there on the mouse move. The next thing I'm going to do is scroll. And you'll notice when I scroll, it only fires an event when I'm finished scrolling. So I'll do a short scrolls, long, scroll the whole page. It only fires that one time. The next one is the resize. Notice the number as I resize this page. Something else you can notice is a little bit of, it's called jankiness. If you notice as I go in and out, it doesn't respond perfectly. That's because every time I do it, there's a number of these JavaScript functions that are being executed, and it takes up some of these CPU cycles for the repaint and the relayout to happen. So we can go ahead and look at code for that. Alright, so I've got some sample code, some styles, just the dummy data there. Here's where it happens. Let's see, right here, 146 through 150 is the resize event. You can see there's nothing bound, or there's nothing wrapping that function. It just is attaching a function straight to the resize event that's being added to the window and incrementing that little resize counter. The next is debounce, which is being attached to scroll, which you could see that on 170 right here. Instead of passing in an anonymous function, we're passing in an anonymous function wrapped in this debounce function with a delay added to it. And what that'll do is it'll hold the function from being executed until those events have stopped being fired. The next one is a throttle. You can see right here we did the same pattern. We wrapped the anonymous function being passed into the event listener. We wrapped that in a throttle, which it doesn't stop it from happening at all until the end, but it will limit it to every certain number of milliseconds. I've passed in right here 500 milliseconds. So every 500 milliseconds this will happen, even if mouse move is being fired 100 times a second. Okay, the next tip is to implement browser caching. So think about the number of assets required to download and render a web page. There's the HTML. You might have any number of images, fav icon, JavaScript, CSS, images, analytics, number of things. It's not surprising to see 50 to 80 assets being loaded all in all. Now most of these, ask yourself the question, is it important the user downloads a new copy of this every time? Or has anything really changed, in my logo between page views? Probably not. So you can implement browser caching by two tags, two headers. And these headers are sent from the server with the response. These two tags are important. They both serve different purposes. Cache control is a number. It's a number of seconds or milliseconds until the browser should ask for a new copy of that. So you could put cache control and put 360,000, and your browser will download the logo, and it's not going to ask for a new copy of that logo until 360,000 of those seconds have elapsed. The second cache header that's important is the e-tag header. The e-tag header provides a GUID similar to a hash of that file, and it's a way that the browser can ask the server if anything's changed without having to send or receive the entire image or the entire CSS file. And so if you think you have an image, it might take 50 kilobytes. You have an e-tag header of random text or hashed or something like that. It's only a few bytes. You can send the e-tag to the server and say, hey server, did this change? The server says nope, keep it. So you still have to do that network request. However, you're at least not doing a network request for the entire image or CSS file or HTML or what have you. You're just sending this teeny string up and it's sending it back to you. Now, one comment that was made in the presentation that's important to bring up again is that this can come back to bite you if you have load balancing between different servers. In that different servers may have different e-tags assigned to each of those assets. And so if you're load balanced, you might be hitting server A for one page view and server B for another page view. And those e-tags on the server aren't going to match, so you're going to have to download a separate one every time. So this is something you want to implement if you have control over the server, the specific server that you have those cached on. All right, the next performance strategy is compression. We use zip files all the time, zips, tars, zar. We all understand how files can be compressed using the mathematic compression algorithms, and then uncompressed or inflated when needed. Browsers and servers have the same transaction they can do. A server can zip a file, send it to the browser, and the browser can automatically unzip that file. And if you look at the screen, for example, that first request, the bottom number, 45.7 kilobytes, is the unzipped. That's the real size. However, 12 kilobytes is the size that was actually sent on the network. That's the zipped size. So if you look, total up, 45, 32, 37, 91 versus 12, 8, 9, 32. The size of these zipped files is, in all cases, I think it's just about a third. I mean, so huge performance and network utilization gains. Now, there's one gotcha with this. It's been around since forever. I mean, this is the dawn of time, right? Internet Explorer 4 had gzip compression. but you still have to enable it on every server you use it on. This is an example of some code required to enable gzip compression if you're using Node and Express. If you use a different server, for example IIS or a Windows server, you'd go into your IIS, find the compression icon, and check the checkbox for enabled gzip compression. So some use configs, some do it through code, some do it through a GUI, different strokes for different platforms. Once we're cached on the browser, we are zipping those requests. The next step is to cache our files and our responses on the server. So think about what a page has to do, or what a server has to do before it delivers a page. It's going to receive a request, maybe make a third-party API call, access your database, find the template, munge the template and the data together, and then return that to the user. Now, by caching, what you can do is once you return, right before you return it to the user, go ahead and save that response somewhere. Save it on the file on the file system, save it in memory, and then the next time that page is asked for, or that asset is asked for, you can just check and then send them the copy from the file system or from memory. So some pseudocode here that would do that is your server receives a request for page 2, checks to see if it exists. If it does, return it right away. If not, build it from the database and from your templates, then save it, and then return it. So the next time it comes around, it'll be saved and it can return it right away. Now, this is easy to implement. However, I wouldn't put this in a production system. This is something that you could do just to learn about caching. This doesn't take into account cache invalidation, which can be difficult doing it based on time or doing it based on the magnitude of changes. We do, however, have a lot of options. There are some third-party caches. Varnish is popular. It's a middleware that can sit adjacent to your application and cache any responses. You can configure that to be implemented in however you want. It's used by some really big places. You may have heard of Facebook, Twitter, New York Times, Vimeo. Memcached is a different type of cache on the server. It can cache objects and you would access it programmatically. So if you received a response from your database, you could ask then memcache to go ahead and save that. Say, this database call key equals this result. Then next time you need to ask for it, it'll get right from memcache instead of asking it from your database. Another type would be like a hardware appliance. We have bluecoats available internally, and if you want to use that, you can talk to your ACE or your portfolio architect and get more information. But it's relatively simple to enable any of these caches for your application. Memcached is also available internally. We have a memcached instance on Cloud Foundry that anyone here can access. All right, the next tip is to understand the timeline and profile your JavaScript. Now, of any of the tips, I think this one deserves its own talk. You can get really in-depth into how this works. But something to keep in mind, or kind of the overall summary, is that your browser has a single track mind. Now, let me re-say that. Browsers are multi-threaded. However, tabs are in general single-threaded, or at least they work in a way that is synchronous. So as every frame or every tick, your JavaScript is executed, then the style is applied to those elements. Meaning if your JavaScript changes width or something like that, it's going to apply the style to an element. Then layout occurs. Layout is the process where all of the elements are geometrically laid out in a way that they'll be shown on the page. So if you change the width of something, that might change the wrapping of a different element and knock everything else, pixels down the page. That needs to be calculated mathematically. The next step is paint, where that layout information is sent to the CPU or the GPU, and an actual image is drawn. The specific colors and pixels are created. Composite is where those layers are put together and placed on your screen. Okay, that's a lot to take in. There's a demo though that should show you how how this can help or hurt you. I'm going to go ahead and show the code first for this demo. All right, we've got a web page that has one box and several other boxes. It's simple, but it's supposed to be representative of a simple web layout. Now, using JavaScript, we're attaching an event to a button, and when that button is clicked, we're retrieving an element, that first box, and then in a loop, increasing its height. You look on line 61 here. We're changing the height to be equal to the loop iterator. So it would be starting at 0 up to 99. The line next to it, we're asking JavaScript for the new height of that element, and then putting that height out to the log. So I'll go ahead and show you what this looks like. So open up your Chrome developer tool. All right, mine was really small there. Go into the timeline tab. The timeline, well, it's just what it sounds like. It's a timeline. It can record and then present to you the data that's collected about events that are fired, JavaScript that's executed, layouts that occur, paints that occur. So I'm going to go ahead and record. Go ahead and push my button. You can see the div change height there. Go ahead and stop recording. Now we're presented with a horizontal timeline of the events that happened. And you can see there's a pretty big something that happens right around 300 milliseconds. So we can zoom in here. And we're zooming in on the time. Okay, so you can see from about 300 to 360 milliseconds, there was an event that was fired, there was a function call that happened, which called an anonymous function, and that anonymous function did lots of JavaScript and lots of layouts. Remember, from the slide, purple is our layout, right there, style and layout. Now, I wonder why it needed to do all these layouts. Why wouldn't it just execute the JavaScript and then call these layouts intermittently? Well, remember the timeline. JavaScript execute first, then style, then layout, then paint, then composite, always in that order. They can't skip back and forth. Well, let's go back to the code here. So what we did was, in this loop, we assigned a new height to an element, and then we retrieve the offset height from that element. Now, to get an offset height, that means the height of the element from the top of the page. Well, if the height of the element, or the height of the element from the top of the page, is changing, it's not going to know that. The document isn't going to know that until all of those other elements have been put into place by the layout function. So essentially, each iteration of this loop, we're setting the height, then we have to break out of JavaScript, do a layout, and then return that data back into JavaScript. And so you see, that's why we have this thrashing going on. So you see JavaScript layout, JavaScript layout, JavaScript layout, JavaScript layout. And another important consideration to take away from this is that you'll notice the box itself didn't animate, even though we're doing it in a loop and we're just increasing the height one time every loop. Remember, JavaScript happens first, and then layout, and then painting happens at the very end. And so what's going to happen is JavaScript's going to go through this loop. Okay, the height's 1, it's 2, it's 3, it's 4, all the way to 99. And then when it's finished doing that, then it's going to send everything to the CPU to be painted and shown up on the screen. So you can see this big paint event at the very end, here and here. That's why we can't animate things in loops like that in JavaScript. We need to use We need to use CSS animations. We need to use other ways of animating that are less intensive on the CPU and, frankly, possible in JavaScript. So we can make this a little better. What I'm going to do is I'm going to comment out these two lines. So now we're only going to increase the height of the div, and then at the very end, after this is run, then we'll output that in the console. Let's see what happens by moving this outside of the for loop. We've modified that code so the layout portion will happen after the style is changed on the element. Let's go ahead and rerun that timeline and see what happens. Record. Push my button there. Stop the recording. All right, we can right off the bat notice there's a lot less that happens here. So let's zoom into this event. So you see this is much smaller. The function is, let's see here. Okay, the function is called the event. The anonymous function passed into the event listener happens. It does one layout, executes a little bit of JavaScript, and then paints it back on the screen. So you can see just by minimizing the work going back and forth between JavaScript and layout, we've dramatically decreased the size of the JavaScript footprint in execution in the browser. Okay. All right, the next tip is to serve assets that are static from their own domain. So take a step back, think about the overall architecture of the web. Cookies are important. Without cookies, we wouldn't be able to store authentication tokens on users' computers. We wouldn't be able to remember preferences. We wouldn't be able to personalize content or do any number of things. Now, when a request is made to any domain that has cookies, all of those cookies are sent with each request, which makes sense. If you need your server to authenticate a user, you're going to need to send those cookies along with the request. But there are many assets that don't need server authentication or personalization, mostly static assets like images, JavaScript files, CSS files, or other media. These are files that can exist standalone outside of the requirements of this architecture model. So one way to save on size of request and response is to serve images or CSS files or static assets of any kind from a separate domain. When a domain doesn't have cookies at all, there's none to send, and your performance download weight and receive weight decreases, improves your performance. So cookies are relatively small, right? A few bytes, maybe a few hundred bytes. But think about your average page. You might have 80 requests to a server between images, font files, the HTML document, follow-up, JSON requests, asynchronous scripts that are loaded, style sheets. Well, if you're sending 100 bytes, relatively small, a cookie, but you're sending that with each and every request, those can add up, and add up in terms of just the sheer amount of data that's downloaded. So one way to mitigate that is to move those assets to a separate domain. It doesn't actually have to be a separate application. You can create a separate domain that then will like proxy into your application and serve those assets just from the server or from that folder, as if it was a separate application. It doesn't need to be aware of the rest of it. Now, if you're working on church products, we've got a surprise for you. We have domains that are set up in each testing lane, stage lane production environment, and these are essentially free for anyone to use. In fact, we'd love it if people did use them because they come with an enormous amount of benefits. So if you're interested, you can talk to Aaron Barker for more information about those assets or those domains that are available. Another benefit is there's some integration with Stash, our internal source code repository. We can set it up to push to Stash, and using a hook, automatically build out and push assets to these static cookieless domains. All right, the next tip is to use a content delivery network. Think about the global nature of our audience. Users are all over the world. You're going to have full-blown stakes missions, even separate ICS locations in some of these far-flung reaches. A request from Australia, how does that get routed? Does that come, does that come underneath the Pacific Ocean, or does it come up through, China to Europe to under the Atlantic Ocean? There are a number of ways that a request can get from Australia, Africa, China, South America, all the way back to our single data center in Salt Lake City, or at BYU, whatever data center your stuff is hosted on. Content delivery networks essentially take snapshots of those files and can host them around the world. So if you're in Europe, you're only going, a few hundred miles away up to, somewhere in London or something like that. And the number of different servers on here is just an illustration. In reality, CDNs can have anywhere between hundreds to hundreds of thousands of separate servers. This is a list of popular commercial CDNs. Akamai, I believe, is the industry standard. It powers Facebook and YouTube. Amazon has an offering. Rackspace has an offering. Cloudflare is fun. They're smaller, but you can actually have a free option. I run my blog through Cloudflare, and in about 5 minutes you can set up any site to, you point your DNS entry to Cloudflare, and then point your Cloudflare DNS to your site, and it'll proxy all those requests and do and have kind of a built-in free content delivery network. So like I said, Akamai is the industry leader, I believe. Microsoft has one on the Azure, their Azure infrastructure offering as well. Didn't include this on this slide. Ta-da! If you want to use our internal static cookieless domains, those are automatically routed through Akamai and go out to hundreds of thousands of servers all across the world, literally. And that's something that you can use for free. We have a commercial, license and enterprise agreement with them, and we serve terabytes and terabytes of video data and other content through Akamai. And so if you want to put data from your site up on Akamai, that would be essentially free to you, and I'd urge everyone to take advantage of that. All right, the last two tips are not appropriate for everyone. They're specific for the needs of your site and the architecture that your site has or can implement. So the first is flushing partial responses. This is appropriate for sites that serve dynamic, personalized content, applications. Think about, here's another step back, think about architecture situation. What sequence of events happens when you make a request to a server? You type it in your browser does a DNS lookup, it does some network time that could bounce around all over the world until it finds the server. The server builds that page, sends it back over the network to you, bouncing around the world. You receive it, parse it out, you then go in and make separate requests for CSS, JavaScript images, things like that. Just within building a page, there can be lots of other things that happen. There's routing, authentication. You might make a call to an external API. You're going to do database calls, looking up templates and building that data. So these are all pretty synchronous processes. You need to authenticate a user, then make a database call. And even if they're not synchronous within themselves, they're synchronous to the nature of the request, or the big picture of the request. Doing network time, building the page on the server, and then more network time delivering it. So in this tip, flushing partial responses, we break up these pages into little chunks in our application that we can send down the network at different times. Instead of building the page all at once and then breaking it up into packets and flushing it down the network, we can force these packets to happen on our timeline. So one way to do that would be build the head of your document, which includes the header, styles, title tag, and before you do that, you're doing user authentication, and then you send that on the network. And while that's traveling on the network, you then, on your server, you're still there, you make a database call, you retrieve content, you look up personalization information, you package that up, and then send that on the network. And you finish your page, send it on the network too. And these are all happening at different intervals in a pipelined way. And when the user receives that, looks like this. You get your first request is going to come in, or your first flush is going to come in first. The head of the document, it contains CSS. The browser can parse that and then start downloading CSS right away. The second set of packets come in. It contains the body of the page. Your browser can render or can parse that into a DOM and render that onto the page. Your last set of packets comes in. It contains script files. The browser retrieves those and makes hopefully asynchronous calls for those script files. This is surprisingly easy to do in some technologies. If you're using the MVC framework built into ASP.NET, you can call response.flush. If you're using JavaScript, there's a way to, or Java, you can do that. PHP, there's an easy way to do that. Node, some argue that Node will do that automatically, but that's more complicated than this presentation. In MarkLogic, which is a technology we use here frequently, MarkLogic unfortunately can't do this because of the nature of the way MarkLogic builds XML documents. It can't push down partial responses. So again, this is inspired by, it's really inspired by CPU pipelining, where you could get an operation into the CPU and then send that off to the circuit, and at the same time have another operation queued up right behind it, instead of waiting for it to complete. So we do the same thing. We do an operation on the server, and we send that on its merry way down to the client, and then we do more operations. And while we're still working on the server, the client can then be making requests of its own. So like I said, this is appropriate for real dynamic, real personalized applications. This does not make sense for an application that you have cached. If you have content-heavy apps or websites, I don't know if it gives anything, because you're going to have these pages cached and they're going to be on a CDN anyway, and so it doesn't make sense to be hitting the server for every request. All right, here's another and a final tip is to use an isomorphic architecture. We talked a little bit about isomorphism at our last Donuts.js meeting. Isomorphic architecture, just to summarize that for those who may not have been there, is it's the method of using a common language between two different environments. And on the web, that means, well, our common and only language we can use on the web is JavaScript. So we use JavaScript on the server. Now, one of the benefits of this are, if we're using JavaScript on the server and the client, we can have a shared template that can be rendered both by the server or on the client. We can also have shared logic. Business logic could happen on the client, for example. We could validate on the client, send a request, and then validate that on the server as well, using the same business validation logic. So I'm going to give a demo, and this is a live demo. We all know how those work, so we're going to go ahead and try our best here. This is an isomorphic application the church history team has been working on, and it's going to be out in production hopefully in the next 2 weeks. This application, just while this is loading from our test environment, is a database of pioneers that came across the plains in the Mormon pioneer, the migration to Salt Lake City. So we list a number of these pioneer companies here. And I'm going to go ahead and show you what network looks like. So if I load this page, I'm loading it normally as any user would, or as any server, or like a crawler or spider would. This is how Facebook sees the page when it crawls it. This is how a user sees the page when it's sent to them in an email and they have to load it up. It's just a normal standard page refresh. And if you notice, in my network tab, there were 570 kilobytes transferred. I have the cache disabled for this example. And it made 76 requests. It took 3 seconds, which is a pretty long time. There's a lot of data on this page that we had to render from the server the first time. We don't have caching set up yet. 570 kilobytes loaded. Now here's the magic. Any of these pages, the data that builds them is JSON on the server. So why can't we use our own URL as a JSON API? Well, that's it. We can. We've used the own URL of each resource as an API to retrieve the data of that page. And this is the data that's responsible for building the page. We use JSON as our data store format, and handlebars as our templating library. So on the server, it gets this data from a database API, combines that with handlebars, builds a page, and sends that down to the user in the form of HTML, just like we did here. So here's where isomorphic magic comes in. If each of these pages are available as JSON, and the server used handlebars to build the page in the first place, we can make an AJAX request for the link to get it as JSON and rebuild the page using JSON and handlebars on the client, simultaneously changing the URL using the HTML5 history API. So I'm going to go ahead and clear my tab of those network requests and pick one of these companies and pay attention to what requests come through. Looks like there were 9 requests made, a few of them for some social icons displayed on the page, his image, the favicon, and then this request for the JSON of the page. So what we did is we listened to any link clicks we listened to in JavaScript, stop that link from happening, and then use JavaScript, get the page in JSON, rebuild it on the client. And you can see what a difference that made in terms of page weight, 37 kilobytes. And most of that, honestly, was the images. The actual data of the page was only 5 kilobytes. So I'm going to go ahead and go back to this page. I'm back too far. Go ahead and clear that again. And here's some more magic. If you notice, I clicked on that page. It took me straight here, and there was no network request for the JSON. And what we can do is, because we're making these with AJAX, we're caching these in session storage. I'm going to go ahead and go to resources, local storage, excuse me. Yeah, session storage. So you can see each of these requests we're caching the data, which means that subsequent requests, we never even have to make network calls. We can load the data of the page from session storage, build the page, and show it to the user instantly, which has the nice side effect of this application becoming an offline app for any pages that you've already browsed. So if you're using this in a less than ideal network location, you can lose your connection and still be able to navigate back and forth between pages that you've already loaded in the past. Thank you. It's been an honor to present to Donut.js. We talk about performance in the Slack channel, and if you want to learn more about performance, I have a blog where I publish thoughts about performance and other web development stuff in general. So again, this is Mike Jasper, and go make great, fast websites. Thanks.